Hello everyone, I am Ankita Tiwari, pursuing my doctoral from Department of Pharmaceutical Sciences, Dr. H.S. Gaur University, Sagar, MP, with an interesting and learning episode of B.Pharm on the important unit of Diuretics in Medicinal Chemistry 3rd, 6th semester, which is scripted by Pradeep Nirbhavne. Currently, he is pursuing his doctoral at Punjab University in Pharmaceutics Department, specially on drug delivery and nanotechnology. Module 1, Introduction of Diuretics. Module 2, Classification of Diuretics. Module 3, Site 1 Diuretics. Module 4, Site 2 Diuretics. Module 5, Site 2 Diuretics A, Amino-benzoic acid derivatives. Module 6, Site 2, 4-amino-3-pyridine sulfonyl ureas and phenoxyacetic acids. Module 7, Pharmacokinetic properties, side effects and drug interactions of Site 1 and 2 diuretics. Now let us start with Module 1, Introduction of Diuretics. A diuretic is defined as a chemical that increases the rate of urine formation. These are the drugs that are used to reduce the abnormal accumulation of excess fluid in the body. These diuretics can do this by eliminating the excess fluid through increasing the volume of urine excretion. Diuretics, in fact, act to modulate different processes to reduce sodium and water reabsorption, resulting in increased water excretion. A diuretic usually possesses some combination of natriuretic, that is, chloruritic, saliuretic, kaliuretic, bicarbonate uritic, or calciuretic properties, depending on whether it enhances the renal excretion of sodium chloride, sodium chloride, potassium bicarbonate, or calcium respectively. The primary action of most diuretics is the direct inhibition of sodium transport at one or more of the four major anatomical sites along the nephron where sodium reabsorption takes place. A clear distinction must be made between the use of the terms potency and efficacy. The potency of a diuretic is related to the absolute amount of drug, example milligrams or milligrams per kilogram, required to produce an effect. The relative potency is a convenient means of comparing two diuretics and is expressed as a ratio of equi-effective doses. The potency of a diuretic is influenced by its absorption, distribution, biotransformation, excretion, and inherent ability to combine with its receptor, that is, its intrinsic activity. The potency of a diuretic is important for establishing its dosage but is otherwise a relatively unimportant characteristic. Efficacy relates to the maximal diuretic attainable, which is usually measured in terms of urine volume per unit of time or urinary loss of sodium or sodium chloride per unit of time. Module 2, Classification of Diuretics. Now, as you understand about the term diuretics and its significance, let's see about the different types of diuretics and their properties. Classification of diuretics. Diuretics are broadly classified as mercurials and non-mercurials. However, we are only concerned about the non-mercurials diuretics. These are further classified as Site 1 diuretics, that is, carbonic anhydrase inhibitors. Site 2 diuretics, which are high ceiling or loop diuretics. Site 3 diuretics, that is, thiazide and thiazide-like diuretics. Site 4 diuretics, potassium sparing diuretics, and osmotic diuretics, example inulin and mannitol. As you can see from the figure below, different diuretics have different sites of action and thus they have named as Site 1, Site 2, etc. as per the sequence of sites, which is from filtration to urine excretion sites. Figure, sites of action of different diuretics. Osmotic diuretics, example isosorbide, mannitol. Carbonic anhydrase inhibitors, for example acetazolamide. Thiazide diuretics, examples are chlorothiazide, benzthiazide, hydrochlorothiazide, trichloromethiazide, methylclothiazide, polythiazide, hydroflumethiazide, bendroflumethiazide. Thiazide-like diuretics, examples are metolazone, quinethazone, chlorthalidone and indapamide. Loop diuretics, example furosemide, ethacrinic acid, bumetanide and torsemide. Potassium sparing diuretics, examples are amiloride, triametrine. Then aldosterone antagonist, that is mineralocorticoid receptor antagonists. Examples are spironolactone, canrenone and eplerenone. Table 2, diuretics, sites and mechanism of actions. Class of diuretics, carbonic anhydrase inhibitors. The site of action is proximal convoluted tubule, that is PCT. Mechanism of action, inhibition of carbonic anhydrase inhibitors decreases sodium bicarbonate reabsorption. Class of diuretics, high ceiling or loop diuretics. Site of action, thick ascending limb of loop of Henle. Mechanism of action, inhibition of the luminal sodium potassium chloride transport system. Class of diuretics, thiazide and thiazides-like diuretics. Site of action, cortical portion of thick ascending limb of loop of Henle. Mechanism of action, inhibition of sodium chloride symporter. Class of diuretics, potassium sparing diuretics. Site of action, distal tubule and collecting duct. Mechanism of action, inhibition of sodium and water reabsorption by competitive inhibition of aldosterone, that is spironolactone. Second mechanism is blockade of sodium channel at the luminal membrane. Examples triametrine and amiloride. Class of diuretics, osmotic diuretics. Site of action, proximal tubule, loop of Henle and collecting duct. Mechanism of action, osmotic effect decreases sodium and water reabsorption, increases medullary blood flow to decrease medullary hypotonicity and reduce sodium and water reabsorption. Sodium and water reabsorption decreases because of reduced medullary hypertonicity and elevated urinary flow rate. Module 3, Site 1 Diuretics. Now, let's study in detail about the Site 1 diuretic, that is carbonic anhydrase inhibitors, that is CA inhibitors. They act on the enzyme carbonic anhydrase. Acetazolamide is the prototype of this class. Site 1 diuretics, they are basically carbonic anhydrase inhibitors. Example, acetazolamide. Carbonic anhydrase is located both intracellularly, that is type 2 carbonic anhydrase, and brush border membrane, that is type 4 carbonic anhydrase of proximal convoluted tubule cells. Thus, Site 1 diuretics act on the convoluted and straight portions of the proximal tubule, which are responsible for the reabsorption of first about 65% of the filtered loads of sodium, chloride, calcium and water, 80 to 90% of the filtered loads of bicarbonate, phosphate and urate, essentially 100% of the filtered loads of glucose, amino acids and low molecular weight proteins. Acetazolamide, N5-aminosulfamoyl 1,3,4-thiadiazole 2-yl acetamide. As you can see, the structure of acetazolamide contains thiadiazole as the basic ring. Now let's see about the structural development of the active moieties of this class by studying the structure-activity relationship, that is SAR. Structure-activity relationship. SAR studies involving the simple heterocyclic sulfonamides produced the acetazolamide, the prototype of this class. The sulfomoyl group is essential for in vitro carbonic anhydrase inhibitory activity and for diuresis production in vivo. The nitrogen atom must remain unsubstituted to retain both in vivo and in vitro activities. This feature explains all antibacterial sulfonamides except sulfanilamide, which are capable of inhibiting carbonic anhydrase or exerting diuresis. The substitution of a methyl group on one of the acetazolamide's ring nitrogen yields methazolamide, a product. Within a given series of heterocyclic sulfonamides, the derivatives with the highest lipid to water partition coefficients and the lowest pK values have the greatest carbonic anhydrase inhibitory and diuretic activities. The above figure, that is figure 2, gives you the complete insight of SAR of carbonic anhydrase inhibitors. Now, acetazolamide synthesis. The synthesis of the prototype drugs in various classes are frequently asked in exam. Hence, it is necessary to know in detail about the synthesis of prototype drugs. As acetazolamide is the prototype drug of Site 1 diuretics, we will study about it. Similarly, we will study the synthesis of prototype drugs of site 2 diuretics in their sections. Reaction between hydrazine hydrate and ammonium thiocyanate yields 1,2-bis-thiocarbamoyl hydrazine, which on treatment with phosgene undergoes molecular rearrangement through loss of ammonia to yield 5-amino-2-mercapto 1,3,4-thiodiazole. This on acylation gives a corresponding amide, which on oxidation with aqueous chlorine affords the 2-sulfonyl chloride. The final step essentially consists of amidation by treatment with ammonia. Now let's study about the pharmacokinetic properties and uses of site 1 diuretics. Pharmacokinetics. The clinically available carbonic anhydrase inhibitors are absorbed well from the gastrointestinal tract, are distributed to the sites of major importance for carbonic anhydrase inhibition, undergo little, if any, biotransformation and are excreted primarily by the kidneys. All carbonic anhydrase inhibitors attain relatively high concentrations in renal luminal fluid by a combination of glomerular filtration and active tubular secretion and in proximal tubule cells. Uses. The uses are: in the treatment of glaucoma, carbonic anhydrase is the important enzyme in the aqueous humor formation in the eye. Its inhibition reduces rate of aqueous humor formation, which is excess in glaucoma. They have been used prophylactically to counteract acute mountain sickness, as adjuvants in the treatment of epilepsy, to make alkaline urine to hasten the excretion of weak acids. Products: acetazolamide, that is Diamox sequels. The dosage forms are capsules, tablets, injections. Dose is 250 to 500 milligrams. Methazolamide, that is methazolamide tablets. The dose is 25 to 50 milligrams. Dichlorphenamide, brand names are Kevies and Deronide. Dose is 50 milligram twice daily. Module 4. Site 2 diuretics. We have just finished about the site 1 diuretics and studied all their properties. Now let's move towards the class 2 diuretics, that is high ceiling or loop diuretics. These are potent diuretics which are further divided into 3 more classes. Site 2 diuretics, that is high ceiling or loop diuretics. Loop diuretics act primarily by inhibiting chloride and sodium reabsorption over the entire length of the thick ascending limb of the loop of Henle. Sodium-potassium chloride cotransporter in the thick ascending limb normally reabsorbs approximately 25% of the sodium load. Inhibition of this pump leads to a significant increase in the distal tubular concentration of sodium, reduced hypertonicity of the surrounding interstitium, and less water reabsorption in the collecting duct. This altered handling of sodium and water leads to both diuresis and increased loss in sodium. By acting on the thick ascending limb, which handles a significant fraction of sodium reabsorption, loop diuretics are powerful. These drugs also include the renal synthesis of prostaglandins, and this contributes to the renal action, including an increase in renal blood flow and the redistribution of renal cortical blood flow. The effect of the loop diuretics is dose dependent and is largely determined by the rate at which the diuretic is delivered to its site of action. Diuresis is not seen with very low doses. The following figure describes in detail about the mechanism of action of site 2 diuretics. Study this figure carefully for your better understanding. Site 2, the sodium transport systems responsible for the reabsorption of sodium and associated solutes in the water permeable cortical and medullary portions of the thick ascending limb of Henle's loop. The collective actions of the antiluminal membrane bound 1 sodium, 1 potassium, 2 chloride, 1 cotransport system accounts for transcellular reabsorption of sodium chloride in a sodium chloride of 3:6 and the generation of a lumen positive potential that drives the reabsorption of sodium and other cations by the extracellular pathway, which is shown by dashed lines. Diuretic agents that block sodium reabsorption in the thick ascending limb by inhibition of membrane-bound sodium 1 potassium 2 chloride. This class of diuretics is further divided into 3 subclasses according to their structural chemistry. These are 5-sulfamoyl 2-aminobenzoic acid and 5-sulfamoyl 3-aminobenzoic acid derivatives, 4-amino 3-pyridine sulfonyl ureas and phenoxyacetic acids. Module 5. Side 2 Diuretics, 5-sulfamoyl 2-aminobenzoic acid and 5-sulfamoyl 3-aminobenzoic acid derivatives. Now let us see the first class of Side 2 diuretics. This is the most important class as the important drug of Side 2 diuretics, furosemide, falls in this class. A. 5-sulfamoyl 2-aminobenzoic acid and 5-sulfamoyl 3-aminobenzoic acid derivatives. Furosemide is the prototype of this class. Furosemide is chemically similar to the thiazide diuretics. It has a fast onset of diuretic action. The oral form is used for hypertension either alone or in combination with other hypotensive agents, but the thiazide type diuretics are preferred unless there is renal impairment or cardiac failure. The intravenous route is fast acting in emergency situations such as pulmonary edema. Furosemide has an acute hemodynamic effect in such circumstances. Furosemide, that is 4-chloro-N-furfuryl 5-sulfamoyl anthranilic acid. Structure-activity relationship studies, that is SAR studies. The development of the loop diuretics is an outgrowth of the research involving the thiazide and thiazide-like diuretics. There are some important features that are essential for retaining diuretic activity. First, the substituent at first position where carboxylic group is attached must be acidic. The carboxyl group provides optimal diuretic activity, but the groups such as tetrazole may impart respectable diuretic activity. Second is a sulfamoyl group at fifth position, meta 2-carboxylic group is prerequisite for conferring optimal diuretic activity. Third, the activating group, that is halogen, in the fourth position can be chlorine, CF3 or better yet phenoxy, alkoxy, aniline, benzyl or benzoyl group. The substituents at the 2-amino group of the 5-sulfamoyl 2-aminobenzoic acids are extremely limited and no acceptable deviations are allowed on these moieties. For example, only the furfuryl, benzyl and thianyl methyl groups yield derivatives with maximum diuretic activity, and the order is furfuryl greater than benzyl greater than thianyl methyl. However, the substituents at the 3-amino group of the 5-sulfamoyl 3-aminobenzoic acids can be changed without compromising the diuretic activity. The diuretics from the 5-sulfamoyl 2-aminobenzoic acid class include furosemide and azosemide, while the diuretics from the 5-sulfamoyl 3-aminobenzoic class include bumetanide and pyretonide. Figure 4a, which is SAR of diuretics, that is aminobenzoic acid derivatives. Now, synthesis of furosemide. 2,4-dichloro-5-sulfamoyl benzoic acid may be prepared by reacting 2,4-dichloro-benzoic acid with chlorosulfonic acid at an elevated temperature and then carrying out the amidation. This on treatment with furfuryl amine in the presence of sodium bicarbonate affords nucleophilic aromatic displacement of the highly activated chlorine at second carbon, thereby yielding furosemide. However, the protection of the chlorine atom at fourth carbon may be achieved by regulating the temperature of the furfuryl amination. Module 6. 4-amino 3-pyridine sulfonyl ureas and phenoxyacetic acids. We will study the other important molecules of Side 2 diuretics like torsemide and ethacrynic acid. First, see the 4-amino 3-pyridine sulfonyl ureas derivative. Example, torsemide, that is 1-isopropyl 3,4-3-methyl phenylamine pyridine 3-sulfonyl urea. Uses are: torsemide is useful in the treatment of mild to moderate hypertension in doses of 2.5 to 5 mg given once daily. These doses lower blood pressure as effectively as 25 mg of hydrochlorothiazide but without producing diuresis. Higher doses of torsemide, that is 10 to 20 mg, are associated with significant diuresis and are effective in treating edema associated with congestive heart failure and cirrhosis of the liver. Phenoxyacetic acids. Example is ethacrynic acid, which is 2,3-dichloro 4,2-methylene 1-oxybutyl phenoxyacetic acid. Now let's study the SAR studies. Within the phenoxyacetic acid series, optimal diuretic activity is achieved when first an oxyacetic acid moiety is placed in the first position on the benzene ring. A sulfhydryl reactive acryl oil moiety is located para position to the oxyacetic acid group. C. Activating groups, that is chloride or methyl, occupy either the second and third positions. Alkyl substituents of 2 to 4 carbon atoms in length occupy the position alpha to the carbonyl on the acryl oil moiety. And E. Hydrogen atoms occupy the terminal position of the carbon-carbon double bond of the acryl oil moiety. Now let's study the biotransformation. Ethacrynic acid is biotransformed by a pathway completely different from that of furosemide or bumetanide. Ethacrynic acid alkylates the thiol group of glutathione in vivo, and the resulting conjugate subsequently is converted to the ethacrynic acid cysteine and ethacrynic acid N-acetylcysteine, that is the mercapturic acid conjugates. Ethacrynic acid cysteine is quite unstable in vivo and in vitro. It readily releases cysteine and ethacrynic acid. Ethacrynic acid glutathione and ethacrynic acid cysteine are equiefficacious diuretics because of the aforementioned interconversions. Approximately 2/3 of the ethacrynic acid appears in the NT in the various forms cited. The remaining 1/3 is in the bile. Figure 5 is biotransformation of ethacrynic acid. Now let's study the synthesis of ethacrynic acid. The synthesis of ethacrynic acid is most important and can be asked in exam, as this synthesis involves two important reactions, that is Friedel-Crafts reaction and Mannich reactions. 2,3-dichlorophenoxyacetic acid undergoes Friedel-Crafts reaction with 4-butyryl chloride to yield the corresponding 4-butyryl analog. This is subsequently subjected to Mannich reaction with formaldehyde and dimethylamino, thereby introducing the methylene group caused by thermal decomposition, yields the official compound. Now let's see some miscellaneous side 2 diuretics. These are atozoline and its active metabolite ozolinone musolimide. These are not so important diuretics and not prescribed generally. Module 7. Pharmacokinetics, side effects and drug interactions of class 2 diuretics. Now let's study the pharmacokinetics, side effects and drug interactions of class 2 diuretics in brief in tabular forms. By stating all these properties in one table, one can study about all the drugs in one glance and it is easy to remember. Pharmacokinetic properties of class 1 and 2 diuretics. Drug acetazolamide, trade name Diamox, relative potency not applicable, oral absorption is greater than 90%, peak plasma is 1 to 3 hours, duration of effect not applicable, half-life is less than 6 hours, route of elimination is unchanged in urine. Drug methazolamide, trade name methazolamide, relative potency not applicable, peak plasma is 1 to 2 hours, duration of effect 6 to 8 hours, half-life is 14 hours, route of elimination 20 to 25% unchanged in urine. Drug furosemide, trade name Lasix, relative potency 1, oral absorption variable, that is 11 to 90, peak plasma 4 to 5 hours, duration of effect 6 to 8 hours, half-life 0.5 to 4 hours, route of elimination is 80% unchanged and 20% metabolites in urine. Drug torsemide, trade name Dermadex, relative potency 3, oral absorption is 80 to 100%, peak plasma not applicable, duration of effect is also not applicable, half-life is 0.8 to 4 hours, route of elimination 30% unchanged and 70% metabolites. Drug bumetanide, trade name Bumex, relative potency is 40, oral absorption is 80 to 100%, peak plasma is less than 2 hours, duration of effect is 5 to 6 hours, half-life is 0.3 to 1.5 hours, route of elimination 50% unchanged and 45% metabolized. Drug ethacrynic acid, trade name Adecrin. Relative potency 0.7, oral absorption is greater than 90%, peak plasma is 2 hours, duration of effect is 6 to 8 hours, half-life is 0.5 to 1 hours. The route of elimination is 30 to 50% unchanged and 30% mercapturate. Table number 4. Comparison of two classes of diuretics with respect to their side effects and drug interactions. Class: Carbonic anhydrase inhibitors, that is Site 1. Side effects: hypokalemia, metabolic acidosis. Drug interactions: none. Class: Loop diuretics, that is Site 2. Side effects: hypokalemia, metabolic acidosis, hyperuricemia, hypomagnesemia, hypovolemia, hypotension, and dose-related ototoxicity. Drug interactions: hypokalemia potentiates digitalis toxicity, NSAIDs reduce diuretic efficacy, corticosteroids enhance hypokalemia, aminoglycosides enhance ototoxicity and nephrotoxicity. Summary: a diuretic is defined as a chemical that increases the rate of urine formation. These are the drugs that are used to reduce the abnormal accumulation of excess fluid in the body. Diuretics can be classified as carbonic anhydrase inhibitors Site 1, loop diuretics Site 2, thiazide and thiazide-like diuretics Site 3, potassium sparing diuretics Site 4, and osmotic diuretics. Site 1 diuretics act on carbonic anhydrase and inhibit it. Their site of action is proximal convoluted tubule. The drug in this class is acetazolamide. It is used in the treatment of glaucoma. Site 2 diuretics act on loop of Henle. The drug in this class are furosemide, torsemide, and ethacrynic acid. They are used in the treatment of mild to moderate hypertension. Thank you.